So this is kind of an overall summary. We did F equals ma yesterday to start. And we derived the inertial velocity as Vk plus this kappa omega Earth rate in the matrix form times this position vector to the center of mass from the Earth center. So you should be able to do that. I skipped a couple steps in there. I let the inertial distance be the Old McDonald's Farm, our EOIO, and then rho k from that. So make sure you can go from here to here, I would say, without looking at your notes, be able to derive this. Then you take the next derivative, and so if you differentiate inertial velocity with respect to inertial space, here's the head fake. You've got two terms here, and this is the head fake that's not in any book. This is the only time you're going to hear it, in fact. You take this first vector, and you apply Coriolis with respect to the body axis on this vector. You take the second vector, and you apply Coriolis theorem with respect to the Earth. That's the head fake. Otherwise, you'll get your own individual equations of motion, which will be right, but which won't be in any other book. So if you take Earth reference velocity Vk, differentiate with respect to body axes, you get Nelson's equation, which he just gives out in his book. If you look at the reading assignment, that's what he says. So you'll have an approximation here that he doesn't. He keeps an equal sign, but you know that that's an approximation for Nelson. Because there's another term over here that he's forgotten, and that's the differentiation with respect to your Earth of this second term over here. So I left that in this form, and I'll let you go through that to make sure you can get this second term and end up with what we call the FEN. So when we were done, we called this guy over here the fundamental equation of navigation, the FEN. It is correct out to 8 decimal places. So make sure you can get to this from this system. Now notice this little g popped out of nowhere, and that's what I wanted you to see, is that the little g comes from separating gravitational forces out of the summation of forces, and then taking omega squared r and encompass and get with the little g. And that gives us plumb bob gravity instead of big gravity from the center of the Earth, because we're rotating. If you were at the equator or at the North Pole, then big G and little g are going to be the same. But if you're somewhere at some latitude in between, northern and southern hemisphere, there'll be a slight deflection of the vertical due to omega squared r. And that gives us our local plumb bob gravity g, which is in the fundamental equation of navigation. Because this is how you would align an inertial platform. It would be aligned until the accelerometers said that you were locally horizontal. Okay? And then again, this is, as a side note, you might in the big G term, you might have moon, you might have other masses that you'd have to take into account other than just the Earth. Okay. So that's where we were yesterday. Satellite in orbit for the Earth, actually he's orbiting this way. We've got the CV0 that he's carrying we're carrying the north, east, and down east, so I, J would give us K, but we're using the orbital plane instead of a meridian line. There's velocities along the stability axis, so that small angle there that you used on your exam to get your direction cosine matrix is going to give us the velocity in the I direction. That velocity divided by Ri, the inertial radius, is going to give us theta dot. And if I put it in the V0 system, I see that the theta dot is negative along J, right? Because J is this way, and if I put my fingers that way, my thumb is going into the board, so it's minus J is giving me the theta. That gives me this angular velocity, and now I apply Coriolis theorem to get the inertial velocity in V0 coordinates. And that gives me dv dt of minus Ri plus the cap omega. And the cap omega, given City's notation, omega x, omega li, omega z, that's going to become, for our orbit, 0 minus theta dot and 0. And if we plug into the formula for the cross product, we get zeros in the diagonal, minus z component, y component, minus x component, and then the skew symmetric reverses the sign across the diagonal. You really need to remember that just for this class. When you get out of this class, you just remember how you go look it up. But for this class, you really know how to do this skew-symmetric matrix given the angular velocity vector. Or put it in your pocket or something. So I'm going to substitute these in here, and we'll get an expression then for our inertial. At the top, I take my velocity vector, put it in orbital coordinates, differentiate it with respect to inertial space to get the forces or the acceleration. I can drop the subscript since I'm in the same coordinate frame, purely differentiate Ri theta double dot plus Ri dot theta dot. Then I put the cross product in matrix form, and I only have the y component to worry about. That's omega y, that's minus omega y. I multiply it by the inertial velocity vector, and that's going to give you this term over here. When you add it all up, you're going to get this term for the acceleration in space. Sum of forces on a satellite is this expression in space, and that's compared with city. I'll leave it for you to go look in the city book and see that's exactly what he gets for a totally different way. What city does is he uses the pure derivative. He only uses the pure derivative, but what do you have to do if you use the pure derivative with the vector? You have to differentiate the basis vector. You see what I'm saying? So if you're differentiating a vector along JK, that vector would be the derivative times JK plus that number times JK dot. You have to find JK dot, the derivative of that unit vector. This allows you to skip all that, this notation. So you might think that the city way is easier. I'll leave it up to you. He derives it in about 1 or 2 pages of his book. I'll leave it up to you to decide which way is simpler. What we've done here, let me recap, yesterday and today, is 1/2 of the heart of 420. This is why we do 420, so that you get these equations and that you see that they're valid anywhere and at all times. And I want you to be comfortable, I want you to be confident, if not comfortable, in going through this and seeing how these things are set. Certainly I would expect you to be able to give me the omega vector matrix given the omega vector. Things like that. Okay. You kind of see what you would be responsible for, what you should know. And again, use the reading assignment that's covered for this week and next week just to boost on what I've done in class. There's a lot more in there. There's a lot more in city. City actually goes into Kepler's equation.